All right, today we're going to talk about absolute extrema as it relates to applications of derivatives. And this is one of the most important applications that you're going to see because absolute extrema refers to the absolute highest y value of a function and the absolute lowest y value of a function. So those values are actually guaranteed by something called the extreme value theorem. And it says if f of x is continuous on a to b, that's important, then f of x has both a maximum value and a minimum value on that interval. In other words, if you draw a graph and it's closed, meaning you don't have arrows at the ends, you have endpoints at the ends, something like, say, this graph is guaranteed to have a highest point somewhere up there and a lowest point somewhere down there. So one thing that's important here is what I said, this word continuous is really important. So continuity must exist for this theorem to hold. And for the extreme value theorem, we're always going to be looking at a closed interval. If it's a closed interval, it's guaranteed to have a highest point and a lowest point. Now, one other thing is I italicized this word value because the word value implies that we are interested in the y value. The value of the function is the y value. Now, the extreme value theorem holds for closed functions on continuous intervals, but I can also look at extreme values on an open interval. It's just not guaranteed to have a highest and a lowest. So if I look for possible extreme values on an open interval, there might be 2, 1, or 0 extreme values. I might have a highest but no lowest, or a lowest but no highest, or one of each, or none. So we're going to look at some graphs that do that down here. So as we come down here, we're going to start to sketch graphs of functions on closed intervals where the absolute extrema occur. First at a peak and a valley. So a hill and in a valley, I'm going to have my highest and my lowest point. So I'm going to start at an endpoint. There's my highest. There's my lowest. If I come back up and stop, there's my highest point at a peak and lowest point at a valley. If I want my absolute extrema to occur at endpoints, I can have a graph do whatever it wants as long as one of them is lower than the rest of the graph and the other endpoint is higher than the rest of the graph. I could also make a different one with just like a straight line. There's a highest, there's a lowest. Okay. And then last but not least, if I want my absolute extrema to occur one at an endpoint and one at a peak, I can have one have a peak up here and the other be down here at an endpoint. Okay. Now, the extreme value theorem doesn't say that something has to be differentiable. It says that it has to be continuous. So as long as I draw it without picking up my pencil, I'm good to go. So if I want to draw it at points where the derivative doesn't exist, I'm thinking about cusps or corners. So I have to go to a highest point and then have a sharp turn, go to a lowest point, sharp turn again. This would be the highest, that would be the lowest, even though the derivative doesn't exist there. And then last but not least, there was that idea of both things can occur at the same value. So here's my highest point, and if I never change from that, it's still my lowest point. Okay? So any horizontal line still conforms to the extreme value theorem, but the highest point and the lowest point are actually the same y value. All right, now, sketch a graph of a function on an open interval, which means that I'm going to have arrows at my endpoints or holes at my endpoints. So I want you to try this one on your own, sketch a couple graphs, and then come back here and see if yours actually follow the right rule. Okay, so here's my three, and they are by no means the only three you could have, but I could have one where there's only an absolute max, just a parabola with arrows at the bottom. Both a max and a min can still have arrows, but what they can do is they can follow like a horizontal asymptote, and then my absolute max is at the hill and absolute min is in the valley. And then neither max nor min, I could either have arrows at these endpoints or holes at these endpoints, because technically this increases and doesn't stop, and that decreases and doesn't stop. So that would work, or arrows at the ends of this would work. All right, so after all those drawings, what you're going to notice is that all those absolute extrema either occur at endpoints or hills or valleys or peaks. So absolute extrema can occur at one of two places. They can occur at critical points, and those are when we have peaks or valleys, things like this, or they can occur at endpoints. And to kind of clarify a little bit more, what is a critical point? Well, a critical point has a definition, a calculus definition, so that's a vocab term you're going to need to know. x equals c is a critical point of f if f prime of c equals 0 or if f prime of c does not exist. In other words, a critical point is where your derivative either equals 0 or does not exist. Okay? Now that we've seen all that, and we've said absolute extrema can occur either at critical points or endpoints, to actually identify the absolute extreme values, I just need to identify the endpoints, identify the critical points, and then figure out which one is highest and which one is lowest. Well, if I look at highest versus lowest, I really want to look for the function value. So if the y value of the function maxes out at 50, then that's your maximum value. If it bottoms out at negative 32, that's your minimum value. So if you want to calculate these yourself, step 1 is identify the x-coordinates of the endpoints. Step 2, find the x-coordinates of the critical points. Then find the value of the function at all those points that you identified in part 1 and part 2. So find the maximum and the minimum values of, let's say, this cubic on negative 6 to 6. So first thing I'm going to do is I'm going to basically make a little bank over here of potential points, if I could spell potential points. And the points I'm going to need to test are automatically the endpoints. I'm going to need to know f of 6. I'm going to need to know f of negative 6. And then I'm going to leave room for any critical points here. So I've identified my endpoints. Now I need critical points. Well, the critical points happen on the derivative, when the derivative equals 0 or the derivative does not exist. So it makes sense. I should probably take the derivative. So f prime is going to be 3x squared minus 12x minus 15. I'm going to set that guy equal to 0. I'm going to solve for x, x squared minus 4x minus 5. I'm just doing some arithmetic and some algebra here. And if I solve that, I get x equals 5 and negative 1. So I took my derivative, I set it equal to 0, got 5 and negative 1. Well, those become other potential locations of absolute extrema. So now I just need f of 6, f of negative 6, f of 5, and f of negative 1. Now to save time, I'm going to use the calculator on this, but often on the AP exam you wouldn't have it because this question with a calculator would really just turn into a graphing question. But basically for what we're doing right there, I am going to take a shortcut just to remind you of some calculator tools. If I have x cubed minus 6x squared minus 15x plus 10, and then I want to find vars, y-vars, function y1 of 6. I can just do that. And so I get negative 80. I'm going to do the same thing again with negative 6. So let me pause and I'll get all the values. So take a second. I'm going to pause just to slow this down. All right, so what happened here is that I plugged all the values into my calculator, I got the corresponding y values, and now I'm just going to look at this y value as a list and say, okay, I have the point 6, negative 80. But the point negative 6, negative 332 is way lower than that, so there's my minimum value. And my highest y value right now is 18. So what's the max value? Well, the max value is the y value. So my max is 18, and my min is 332. Okay? So moving on, example 2, same process. So I'm going to put my test points over here. Find the absolute extreme values of this function on the interval from negative 5 to 5. So I need to test f of 5. I need to test f of negative 5. Now I need to find critical points. So f prime is going to be 2/3 x to the negative 2/3. And I want to know when this equals 0 or when it does not exist. Now, I forgot to state that up here, I should really test when this equals 0 or when this does not exist, except this is a polynomial. It always exists, so that wasn't even a possibility. But down here, when does this equal 0 or do not exist? Well, I'm going to rewrite this as a fraction because it's easier to handle some of these equations when you see them as fractions. So this is 2 over 3 times the cube root of x squared. And I want to know when that equals 0 or does not exist. Well, a fraction equals 0 when the top equals 0, and that's never going to happen. And a fraction does not exist when the bottom equals 0, and the bottom equals 0 when x equals 0. So my only critical point is x equals 0. And then I'm going to look at that. I'm going to plug these three values into here, and I'm going to get, let's see, the cube root of 25 plus 4. I'm going to get another cube root of 25 plus 4. And then when I plug in 0, I'm just going to get 4. So what's my maximum value? Well, my maximum value is this. It doesn't matter that it happened twice. I just want to know the extreme value. So my max is the cube root of 25 plus 4. And my min is 4. Okay? Now this one says find the absolute extreme values of f of x equals 6 minus x squared on the open interval, well, half open interval, from -2 to 3. So the rule is still the same. Absolute extreme values can only occur at critical points or endpoints, but in this case, I only have one endpoint. So I'm just going to test f of 2 and see how that is. And then I'm also going to show f of 3, but I'm going to kind of put an open circle here to remind me that, you know what, this can't be the minimum value. I'm just going to compare it to something else, okay? So I have that. Now I need to find my critical point. So f prime is going to be -2x, and I'm going to set that equal to 0, get x equals 0. So another test point is f of 0. So f of 2 is going to be 6 minus 4, which is 2. F of 3 is going to be 6 minus 9, which is -3. And f of 0 is going to be 6 minus 0, which is 6. So what's my highest point? Well, my highest point is 6. 6 is a point on the graph between -2 and 3. That is absolutely my max. My lowest point happens to be -3, but it's not a point at all, it's a hole. So there is no absolute min. So we only have a max for that one. And then last but not least, this one says find the extreme values of that on its entire domain. So the first thing I should figure out is what's the domain of this? Well, the domain of that would be the points where that inside is greater than 0, which is when x is between 1 and -1. So I'm going to test f of 1 and f of -1, but I'm going to remember that those are holes, that function doesn't actually exist there. And now I want to look for critical points. So I'm going to take my derivative, and this is 1 minus x squared to the -1/2. So I'm going to bring down the power, reduce it by 1, and multiply by the derivative of the inside. I want to know when that equals 0 or does not exist. So this cancels with this, and I really have x over the square root of 1 minus x squared cubed. That's going to equal 0 when x equals 0. And this is not going to exist when the bottom equals 0, except when the bottom equals 0, that's not part of the domain anyway. So I don't have to worry about x equals plus or minus 1 at all. My only critical point is 0, because that's when the derivative equals 0. So I'm also going to test f of 0. So f of 1 would be 1 over 1 minus 1. Wait a minute. That's undefined. But instead of thinking about it as undefined, I want you to think about this as a limit. When you're doing these, you're really taking the limit as x approaches 1 from the left for f of x. And as x approaches 1 from the left, I got like 0.99999. So this is 1 divided by a tiny number, which is going to be infinite. And f of -1 is going to happen the same way, and that's also going to be infinite. And f of 0 is going to be 1. So 1 is less than infinity. So 1 is my absolute min, and we do not have an absolute max. All right. Long story short, what I need you to know is when you are testing for absolute extreme values, you absolutely have to test the critical points and the endpoints. Do not forget about the endpoints. You have to test the endpoints. Lots of people just want to jump right to the derivative. You can't do that. You have to test the endpoints. Then you also have to test the critical points. See what has the highest and the lowest value. If you don't have endpoints, think about limits or holes, and then compare your y values across the board. So that's absolute extrema. It was fantastic. We'll talk about relative extrema another day. Bye-bye.